graphical representation of motion. In the previous video, we learned about the speed with direction or velocity and the rate of change of velocity or acceleration. In this video, we will learn to represent the motion of an object on a graph. Graphs offer an easy method to showcase the relation between two physical quantities. For example, during a cricket match, we can represent the performance of a team in a run versus over graph. Similarly, we can represent the motion of an object in a line graph. In a line graph, we can represent one physical quantity like distance or velocity with another quantity such as time. Let's first discuss the distance-time graph. In this graph, let us take time along the x-axis and distance along the y-axis. Distance-time graphs can be made by considering two situations. Either the object moves with a uniform speed or with non-uniform speed. First, we will consider the case of uniform speed. If an object is moving with a uniform speed, we know that it covers equal distances in equal time intervals. We can say that the distance is directly proportional to the time taken. So, let's start by plotting the graph. Suppose the object covers 10 meters in the first 5 seconds. For the next 5 seconds, it covers another 10 meters and so on. Mark the points on the graph. If you join these points, you can see a straight line passing from the origin. Thus, for uniform speed, a graph of distance travelled against time is a straight line. If the magnitude of displacement is equal to the distance travelled by the object, then we can use the term uniform velocity in place of uniform speed. We can also determine the speed of an object from the distance-time graph. The speed of an object is determined by calculating the slope of the distance-time graph. Let's calculate the speed of an object in the previous distance-time graph. Choose 2 points A and B on the graph. Draw a line parallel to the x-axis from point A and another line parallel to the y-axis from point B. These two lines meet each other at point C to form a triangle ABC. Now, on the graph, AC denotes the time interval while BC corresponds to the distance. We can see from the graph that as the object moves from point A to B, it covers a distance 30 minus 20 is equal to 10 meters. In time, 15 minus 10 is equal to 5 seconds. The speed v of the object can be determined as v is equal to distance travelled upon time taken. Speed is equal to 10 meters upon 5 seconds is equal to 2 meters per second. What if motion is an accelerated one? We can plot a distance-time graph for accelerated motion as well. Given here is a table which shows the distance covered by the car in the respective time interval. Can you plot the graph using the data in the given table? Once you plot the points, your graph will look like this. The nature of this graph shows non-linear variation of the distance travelled by the car with time. Thus, the graph shows the motion of an object with non-uniform speed. Now, let's study the velocity time graph. The variation in velocity with time for an object moving in a straight line can be represented by a velocity time graph. Suppose a car is moving at a uniform velocity of 60 km per hour in a certain direction. The velocity time graph of that car can be plotted by considering the velocity at certain time instants. Here, time and velocity are represented along the x-axis and y-axis respectively. As the car is moving at a uniform velocity, the height of its velocity time graph will not change with time. It is a straight line parallel to the x-axis. Earlier, we studied the relation among uniform velocity, time and displacement. That is, velocity is equal to displacement upon time, or displacement is equal to velocity multiplied by time. Hence, the area enclosed by the velocity time graph and the time axis is equal to the magnitude of the displacement. As the car is moving in a single direction, the magnitude of displacement is equal to distance covered. To calculate the distance covered by the car between time 1 hour and 2 hours, draw perpendiculars from the time points on the graph. The velocity of 60 km per hour is represented by the height AC or BD, and the time interval is represented by the length AB or CD. So, the distance moved by car in time interval can be calculated as S is equal to area of the rectangle ABDC, which is equal to AC multiplied by CD, which is equal to 60 km per hour multiplied by 2 minus 1 hour, which is equal to 60 km. Now, let us consider the accelerated motion. Let's first discuss the effect of uniform acceleration on the velocity time graph. In uniform accelerated motion, velocity changes by equal amounts in equal time intervals. Let's suppose the train driver records the velocity of the train starting from rest at each 10-second intervals. Can you plot the velocity time graph of this data? It should look like this. For uniformly accelerated motion, the velocity time graph is again a straight line. We can also calculate the distance covered by the train from the velocity time graph. To calculate the distance travelled by the train in a certain time interval, we have to calculate the area of ABCDE under the velocity time graph. Area ABCDE is equal to area of triangle ADE plus area of rectangle ABCD, which is equal to 1 upon 2 multiplied by AD multiplied by ED plus AB multiplied by BC. Similarly, we can plot the velocity time graph of a non-uniformly accelerated train. The velocity time graph for a non-uniformly accelerated motion can have any shape. In this graph, the current velocity of the train can be less than or greater than its previous velocity. This shows that the motion is non-uniformly accelerated. We can also determine the acceleration of an object by calculating the slope of its velocity time graph. In this video, we learned how to represent the motion of an object on a graph.